Welcome to All in All.
It's great to be here.
Today, we're embarking on, well, quite an incredible journey, really. A deep dive way out there into the outer reaches of our solar system. We're heading to a world that was, a complete enigma for millennia. We're talking about the very enigmatic eighth planet, Neptune.
Yeah, it's a truly captivating subject. And Neptune's story, it's not just about some cold, distant world, is it? It's really a profound testament to human ingenuity.
How so?
Well, its discovery was this brilliant blend of groundbreaking mathematics on one hand and really persistent observation on the other. It kind of defied the limits of just human sight.
Right.
And as we'll get into today, Neptune holds these incredible clues, not only about its own origin story and its, billion-year evolution.
Which is amazing in itself.
Exactly, but also clues to the very formation of our entire solar system, the processes shaping distant exoplanets all across the galaxy.
Wow.
And even, perhaps surprisingly, connections to technologies we use every single day right here on Earth.
That's right. So our mission for you today in this deep dive is basically to pull back the curtain on Neptune's incredible origin story. We want to understand its profound significance in the cosmos, explore its past and present impacts, trace its remarkable evolution over billions of years.
A long time.
A very long time. And finally, discover its, truly unexpected practical relevance to life right here on our home planet.
Yeah, we're definitely talking some surprising facts and maybe some genuine aha moments that might challenge how you think about our cosmic neighborhood.
Exactly. So let's unpack this. Where do we even begin with a story like Neptune's?
Well, maybe counterintuitively, the story starts not with a telescope, but with pen and paper and some very precise math.
Okay, intriguing. So imagine astronomers back in the mid-19th century, right? They're meticulously tracking the planets they know, and they notice something peculiar, something stubbornly persistent about Uranus, the seventh planet out.
Right, its orbit wasn't quite behaving, it wasn't following the predicted path perfectly.
Exactly. These tiny, almost imperceptible wobbles, slight deviations from where it should have been. It was like something unseen was, gravitationally tugging at it.
Yeah, precisely. And what's truly fascinating here is how these minute deviations, these tiny gravitational nudges on Uranus, sparked this, audacious idea, almost revolutionary at the time.
So instead of just thinking their math was wrong.
Exactly. Rather than assuming their calculations were off or that some unknown force was messing things up, brilliant minds in Europe hypothesized that there must be another planet.
A hidden one.
A hidden one, yeah, whose gravity was causing these specific perturbations. And this wasn't just a wild guess, It led to one of the most monumental triumphs of theoretical science.
So who figured this out?
Well, two mathematicians, working independently actually, Urbain Le Verrier in France and John Couch-Adams over in England. They used these discrepancies in Uranus's orbit.
Those little wobbles.
Those little wobbles, yeah. To calculate with stunning precision exactly where this hypothetical eighth planet should be.
Wow. So it was pure prediction, based just on Newton's laws.
Pretty much. Built solely on the power of Newton's laws of gravity. It was an incredible piece of theoretical work.
And the accuracy. Did it work?
It was nothing short of astounding. On the night of September 23rd, going into the 24th, 1846, an astronomer named Johann Gottfried Galle, he was working at the Berlin Observatory.
Okay.
He got a letter from Le Verrier basically saying, hey, look here in the sky.
Pointing their way.
Literally. Galle, along with his student Heinrich d'Arrest, pointed their powerful Fraunhofer telescope precisely where the calculations suggested, and boom, there it was.
Just like that.
Within a degree of Le Verrier's prediction. Neptune.
That's incredible. It's truly humbling, isn't it, that humanity found a planet not by seeing it first, but by trusting the pure logic of mathematics.
It really is. It tells you something about the hidden order in the universe, doesn't it? And maybe the limits of just pure observation without theory guiding you.
Yeah, absolutely. It's a profound moment for science.
Definitely. It showed that our understanding of the universe isn't limited by what we can directly see, even with instruments at first glance. Neptune's existence, predicted before seen, really solidified the power of theoretical physics.
And you have to appreciate how difficult that observation must have been, even with the coordinates.
Oh, absolutely. Neptune is incredibly faint. It's totally invisible to the naked eye, even on the darkest night, because it's just so immensely far from the sun.
Right.
Its discovery really needed a powerful, cutting-edge instrument for the time, like that Fraunhofer telescope, pushing observational astronomy to confirm what the math already showed.
So the discovery happens. The scientific world is buzzing. What next? Did they start figuring things out quickly?
Surprisingly quickly, yeah. The ink was barely dry on the discovery notes when new revelations started trickling in, just weeks later.
Wow.
Think about the excitement. Only 17 days after Neptune was first spotted, on October 10th, 1846, another astronomer, William Lassell, he was working in England with this formidable telescope he actually built himself.
Impressive.
Very. He spotted a moon orbiting this newly found planet.
Already found a moon.
Yep. That moon, we now know it as Triton, though interestingly, it didn't officially get that name until a second moon, Nereid, was found over a century later in 1949.
Huh. So they just called it Neptune's moon for 100 years.
Pretty much, yeah. And then a third moon wasn't found until 1981. So Triton was the first glimpse into Neptune's little system.
And these early observations, limited as they were, what do they tell us about Neptune itself?
Well, they started painting a very basic picture. Astronomers quickly pegged it as the fourth largest planet in our solar system by diameter, roughly 4 times the size of Earth.
So pretty big.
Definitely a giant. And early atmospheric analysis, mostly using spectroscopy, that technique where you look at how light interacts with the atmosphere.
Right, looking for the chemical fingerprints.
Exactly. That suggested it was similar to the other gas giants, Jupiter and Saturn, so mainly hydrogen and helium in the atmosphere. They estimated its cloud tops were incredibly cold, around 55 Kelvin. That's about minus 361 degrees Fahrenheit.
One of the coldest places we know of, I guess.
For sure. And its day length, how fast it spins, they clock that in at roughly 16 hours. Pretty quick rotation.
So those are the basics. Size, rotation, temperature, main gases.
Yeah, fundamental facts. A real triumph for planetary astronomy back then.
But it's crucial to remember the context here, right? Neptune is about 30 times farther from the sun than Earth is.
Immense distance. Almost unimaginable.
Yeah, put that in perspective. Driving a car there at highway speed?
Yeah.
You'd be driving for, I don't know, hundreds of lifetimes.
Easily. And because of that extreme remoteness and the limits of 19th and early 20th century telescopes, a lot about Neptune, its true nature, its complexities remained a deep mystery for over a century.
So for a long, long time, these initial observations were basically all we had.
Pretty much. We didn't get our next really significant close-up look until the Voyager 2 spacecraft flew past it in 1989. A huge gap in our knowledge.
That's a key point. And to really grasp the significance of the 1846 discovery, how it landed back then, it helps to think about what else was going on in the world.
Right, context is everything. Imagine the news of the day happening alongside this cosmic revelation.
So in the U.S., Texas was formally establishing its state government in Austin. Big deal for the young nation.
Yeah, expansion. And the Liberty Bell in Philadelphia actually cracked that year, ringing for Washington's birthday. A memorable little detail.
And internationally, the Oregon Treaty was signed with Great Britain, setting the 49th parallel as the U.S.-Canada border, defining the map.
A huge geopolitical event. On the cultural side,
Go on.
the saxophone. That incredibly distinctive instrument was patented in 1846 by Adolphe Sax.
No way. The same year.
The very same year. Meanwhile, a relatively unknown lawyer named Abraham Lincoln got elected to the U.S. House of Representatives.
Wow. Starting his journey.
Yep. And the U.S. Congress established the Smithsonian Institution, destined to become this huge complex of museums and research centers.
So picture it. All these foundational things happening, shaping nations, culture, tech, politics, and at the same time, this incredible scientific breakthrough is unfolding.
Largely unnoticed by the general public, probably, but electrifying the scientific community.
It's just a remarkable illustration of how human progress across science and society often moves forward on many fronts at once. Simultaneous discovery.
Exactly.
Okay, so fast forward from those first glimpses. Our understanding of Neptune has really evolved, hasn't it?
Yeah.
We used to just lump it in with Jupiter and Saturn as a gas giant.
Right, that was the initial thinking.
But today, Neptune and its neighbor Uranus, they have this distinct classification, ice giants. So what's the big takeaway? Why does calling it an ice giant matter so much?
That distinction is absolutely crucial. It fundamentally changes how we model these worlds, both here and when we look at exoplanets. Unlike Jupiter and Saturn, which are overwhelmingly hydrogen and helium gas, truly massive balls of mostly atmosphere, Neptune is thought to be made up primarily of, well, heavier volatile compounds, things like water, ammonia, methane.
But not like ice cubes, right?
No, not at all. We're talking about these materials likely in the form of a supercritical fluid. Imagine water under such immense pressure and heat that it blurs the line between liquid and gas.
Sort of a dense, hot slush.
That's a decent way to picture it, yeah. A high-pressure, high-temperature, extremely dense state. And these ices, in their supercritical form, surround what we believe is a relatively small, rocky core.
And the clouds we actually see.
Those visible clouds are likely made of various ice crystals, too. Methane ice, maybe ammonia ice, not just hydrogen and helium gas like Jupiter's main cloud decks. And this difference in primary composition really sets them apart.
It really makes you think how much we've figured out, considering how little we've actually seen up close. I mean, the deep interior. We can't see it. Voyager 2 just did a quick flyby.
Right. Comparatively little is known for sure about the deep interior. It's a huge challenge.
So how does scientists model something they can't see that's so far away under such extreme conditions?
It's really a testament to the power of physics and indirect observation. Our leading model suggests that below that visible atmosphere of hydrogen, methane, and helium, there are these vast liquid layers of those same elements, but also deeper layers with more hydrogen compounds, nitrogen, and oxygen mixed in. And then right at the center, that relatively small but incredibly dense, rocky and icy core.
Okay, that makes sense structurally. But you mentioned some wilder predictions.
Yes. Here's where it gets really interesting, pushing the boundaries of imagination. Theoretical predictions for the deep interiors of ice giants like Neptune are, they're pretty wild.
Go on, I'm intrigued.
Scientists hypothesize that the conditions, extreme pressure, millions of times Earth's atmosphere, and temperatures hitting thousands of degrees could lead to some truly astonishing phenomena.
Like what?
We're talking maybe even a surface made out of carbon, specifically diamonds, and other high-pressure, high-temperature crystals forming down there.
Diamond rain. Seriously, that sounds like science fiction.
It does, doesn't it? But the physics behind it is compelling.
How could that even work?
Well, the idea is that methane, which is abundant in Neptune's interior, gets compressed and heated to such extremes that its carbon atoms actually separate out and crystallize into diamonds. These diamonds would then theoretically rain down through the deeper layers.
Have they tested this?
Amazingly, yes, to some extent. Scientists have managed to simulate these kinds of extreme pressures and temperatures in labs here on Earth. Using things like diamond anvil cells or powerful lasers, they've actually created nanodiamonds under similar conditions.
Wow. So it lends some credibility to the idea.
It does. And other theories suggest even stranger things like maybe liquid helium rain or metallic tidal waves, think molten metal oceans sloshing around, or even lightning bolts longer than entire countries.
Okay, my mind is officially blown. Metallic tidal waves.
It's pushing physics to the extreme. But these are highly educated guesses, of course. We infer the composition mainly through spectroscopy, like we mentioned.
Right, the light spectrum.
Yeah, when light reflects off Neptune, we analyze it. We look for those dark lines, the absorption bands, where specific elements or molecules have soaked up particular frequencies of light.
And this method works.
It's been tested extensively on Earth, confirmed by missions to Mars and the Moon. It gives us a surprisingly good, though still rough, idea of the composition and the proportions of different elements.
But still uncertainties because of the extremes down there.
Exactly. The immense pressures and temperatures mean there are still big question marks. It's truly mind-boggling to think about conditions where common elements behave in such extraordinary ways.
So Neptune looks serene, this deep blue marble, but it's anything but calm, right? You mentioned winds.
Oh, absolutely not calm. It holds the record for the strongest winds in the solar system. We're talking speeds up to 2,400 kilometers per hour. That's about 900 miles per hour.
900 miles per hour. That's almost 3 times the speed of sound on Earth.
Yep. Even faster than the winds tearing across Jupiter and Saturn. It's incredibly dynamic.
What's driving winds like that?
That's a great question. Likely tied to its internal heat source, which we'll get to. But Voyager 2 gave us our first close-up look at the effects. It saw these huge storm systems, most famously the Great Dark Spot.
Like Jupiter's Great Red Spot.
Similar in appearance, roughly the size of Earth, but fundamentally different. Unlike Jupiter's long-lived spot, Neptune's large storms aren't confined to a specific latitude. They tend to be quite short-lived.
Oh, really?
Yeah, observations from the Hubble Space Telescope later showed that the Great Dark Spot Voyager saw had vanished just a few years later, and new ones appeared and disappeared within relatively short timescales.
So a much more changeable atmosphere than Jupiter's.
Exactly. It tells us something different is happening in their atmospheric dynamics.
And the blue color, we know it's methane, right? Absorbing red light.
That's the primary reason, yes. Methane gas, CH4, in the atmosphere absorbs the red wavelengths of sunlight, letting the blue light scatter back towards us.
But Neptune's blue seems deeper, richer than Uranus's blue, even though Uranus is also blue because of methane. Why the difference?
That's another great question, and it hints at subtle but significant differences between the two ice giants.
Okay.
The deeper blue on Neptune might be because it has more haze, or maybe a higher concentration of methane higher up compared to Uranus. Or perhaps there's some other unidentified chemical constituent in its atmosphere that's absorbing even more red and orange light.
Still some mysteries there. And the chemistry gets complex, right? You mentioned equilibrium versus disequilibrium.
Right, deep down, things are likely governed by thermochemical equilibrium. Think of it like a stable chemical kitchen, where extreme heat and pressure drive reactions to a steady state.
Okay, predictable deep down.
Relatively speaking. But in the upper atmosphere, the part we can actually see and study remotely, disequilibrium processes take over. Things like transport-induced quenching and photochemistry.
Whoa, okay. Breaking that down.
Basically, sunlight hitting the upper atmosphere, photochemistry, and strong vertical winds dredging stuff up from deeper, hotter layers faster than it can chemically adjust, quenching, really alter the composition up top.
So it's like Neptune has two different chemical zones, a stable one deep down and a wilder sun and wind mixed one up top.
That's a good way to think about it, yeah. And that wilder kitchen is where we see some interesting clues. For example, carbon monoxide, CO.
Carbon monoxide.
Oh,
like from car exhaust.
Same molecule, yeah. It's been definitively detected in Neptune's troposphere, but interestingly, not really on Uranus.
And that tells us what?
Well, the amount of CO observed gives us clues about the deep oxygen to hydrogen ratio. For Neptune, it's estimated to be about 250 times the ratio found in the Sun.
Okay.
Compare that to Uranus, where the OH ratio is less than 45 times solar.
That's a big difference. What does it imply?
It suggests Neptune must have accreted, or gathered, a much higher proportion of oxygen-rich ices during its formation compared to Uranus. Little chemical clues painting a picture of their birth.
Fascinating. And speaking of differences between Uranus and Neptune, here's a big one. The internal heat.
Ah, yes, the temperature anomaly.
Right. They have similar average cloud top temperatures, around minus 230 Celsius, minus 380 Fahrenheit. Incredibly cold.
Freezing, yeah.
But Neptune's interior emits more than twice the energy it receives from the sun. It's radiating significant internal heat.
Whereas Uranus is largely in thermal equilibrium, it radiates away about as much heat as it gets from the sun. Almost no internal heat escaping.
Why? They seem like twins in so many ways. Why would Neptune be so much hotter inside, or at least leaking heat more?
That's one of the biggest mysteries about the ice giants. A leading hypothesis involves a giant impact in Neptune's distant past.
A massive collision.
Possibly. During the chaotic early days of the solar system, such an impact could have completely mixed its interior, stirring everything up.
And how would that lead to more heat escaping?
If the interior got thoroughly mixed, it might create what's called an adiabatic thermal profile. Think of it like, if you stir a pot of soup really well, the heat distributes more evenly and can escape from the top more easily. A giant impact might have prevented distinct layers from forming inside Neptune that could trap heat.
Ah, so Uranus might have those insulating layers, trapping its internal heat more effectively.
That's the idea. Maybe Uranus had a less violent past or formed differently, allowing it to develop a layered structure where heat flow is inhibited by diffusion, keeping its internal warmth locked inside more effectively.
So a single, ancient, violent event could explain this fundamental difference today.
Wow. It's a compelling possibility, yeah. Shows how history shapes planets.
Okay, beyond the winds and the heat, Neptune also has a really peculiar magnetic field, doesn't it? And rings.
It does. The magnetic field is incredibly complex. It's significantly offset from the planet's center by about 13,500 kilometers.
That's a huge offset.
It is. And it's tilted quite dramatically, about 47 degrees relative to its rotation axis.
So it's not like Earth's nice, neat magnetic field.
Not at all. Earth's field is mostly a simple dipole, like a bar magnet, generated relatively symmetrically in our liquid iron outer core. Neptune's field is much more irregular, creating this highly asymmetric magnetosphere, almost like a twisted mess.
What causes that difference?
It likely comes down to where the field is generated. Not in a metallic core, but probably through convection currents within that conducting ice mantle, that layer of supercritical water, ammonia, and methane.
The supercritical fluid layer.
Exactly. That conducting region being further out from the center than Earth's core, combined with Neptune's rapid rotation, might be what creates this complex, lopsided field. A reminder that planetary interiors vary wildly.
And the rings. Not like Saturn's glorious ones, I gather.
No, definitely not as prominent. Voyager 2 confirmed they exist, but they're dark and described more as tenuous ring arcs than complete bright rings. Some parts are denser than others.
Faint and clumpy. How much material are we talking about?
Very little, actually. If you could gather all the material in Neptune's observable rings and mash it together, it would form a body maybe only a kilometer or so across.
Just a kilometer. Compared to Saturn's?
Saturn's rings, if combined, would make something maybe 500 kilometers wide. Even Uranus's rings would form an object tens of kilometers across. So Neptune's are truly wispy.
Why are they so sparse? And why arcs?
Well, they're incredibly dynamic. These rings aren't static structures. They're made of countless colliding particles. There's viscous spreading, angular momentum exchange with nearby small moons. It's complex.
Okay.
And the microscopic dust particles within them have very short lifetimes, hours to maybe millennia, because solar radiation pressure and drag tend to clear them out.
So they need to be constantly replenished.
Exactly. They require permanent sources. The leading theory is that impacts micrometeoroids hitting Neptune's small inner moons constantly chip off dust and debris, which then feeds into these transient ring arcs.
So the rings are basically constantly renewed debris from moon impact.
That seems to be the most likely explanation, yeah. The whole system, atmosphere, magnetic field, rings paints this picture of a world far more dynamic and complex than you might guess from its distant, calm blue appearance.
Absolutely. And this dynamic nature, it isn't just about Neptune now, is it? It's fundamental to its entire history, tied right into the birth of the solar system itself.
Precisely. To understand Neptune, you have to understand the grand narrative of our solar system's formation and its, well, rather turbulent youth.
So we start with the basic picture, the nebular hypothesis.
Right, the standard model. Our solar system formed about 4.6 billion years ago from the gravitational collapse of a piece of a giant molecular cloud, this vast cold cloud of gas and dust.
Most of it became the sun.
The vast majority, yeah. The rest flattened into this spinning protoplanetary disk, like a cosmic pancake.
Okay.
And within that disk, dust grains started sticking together, growing into clumps, then bigger planetesimals through countless collisions, gradually building up the planets we see today through accretion, a messy process.
But they didn't just form and stay put.
Right.
That's where things get interesting for Neptune.
Exactly. The planets migrated, and one of the leading scenarios for how that happened, especially for the giant planets, is called the Nice model.
Named after the city in France.
That's the one where it was developed. This model proposes that after the initial gas and dust disk cleared out, maybe a few 100 million years after the sun formed, the giant planets Jupiter, Saturn, Uranus, and Neptune were originally in a much more compact configuration, closer to the sun, between maybe 5.5 and 17 astronomical units, AU.
Much closer than they are now. Neptune's way out at 30 AU.
Right. And they were more closely spaced. Crucially, beyond the outermost giant planet back then, there was this large, dense disk of millions of small, icy planetesimals, a sort of primordial Kuiper belt, but much more massive.
Okay, so a compact system with a big icy disk beyond it. What happened next?
Well, this compact setup, while maybe stable for a while, eventually led to a dramatic instability event. Yeah. The core idea of the Nice model is that Jupiter and Saturn slowly migrated outward due to interactions with those planetesimals until they hit a critical 2.1 mean motion resonance.
The resonance again. Saturn orbiting once for every 2 Jupiter orbits.
Precisely. And reaching that specific resonance dramatically destabilized the whole system. It pumped up their orbital eccentricities, making their orbits much more elliptical.
So they started swinging around more wildly.
Exactly. And this led to chaotic, powerful gravitational encounters between Saturn and the 2 ice giants, Neptune and Uranus. These encounters literally kicked Neptune and Uranus outward onto much more eccentric, elongated orbits.
Flung them out.
Pretty much flung them towards that dense, icy disk.
That's where Neptune became, what did you call it, a cosmic snowplow?
Yeah, or a wrecking ball. As Neptune and Uranus were thrown outwards onto these wild paths, they plowed right into that dense disk of planetesimals.
Must have been chaos.
Absolute chaos. This wasn't a gentle nudge. They scattered tens of thousands of these small, icy bodies all across the solar system. It basically disrupted and ejected about 99% of the primordial disk's mass.
99%? That explains why the Kuiper Belt today seems relatively empty compared to what might have been there originally.
Exactly. This plowing event, this cosmic cleanup, is the leading explanation for the current low mass of the Kuiper Belt. Billions of icy cannonballs flung everywhere.
And what happened to the planets during this scattering?
Well, as the planetesimals scattered off the planets, Newton's third law kicked in. Every action has an equal and opposite reaction. The scattering caused the planets themselves to migrate.
So Uranus and Neptune moved further out?
They moved significantly outwards, yeah. Jupiter actually moved slightly inward, and this whole process shaped the outer solar system as we see it.
How so?
It led to the formation of the Oort cloud, that vast spherical shell of icy bodies way, way out from the most strongly scattered objects. It also sculpted the current Kuiper Belt and the scattered disk from the less energetic scattering events.
And some objects got caught, right? Like Pluto.
Exactly. Some objects, like Pluto and many others, became gravitationally locked into mean motion resonances with Neptune as it migrated outwards. They ended up in these stable orbital dances with the ice giant.
So Neptune's gravity basically controls a lot of the Kuiper Belt structure.
It really does. Eventually, friction within the remaining scattered disk helped damp down the eccentricities, making Uranus's and Neptune's orbits near-circular again, close to what we see today, a turbulent beginning settling into a grand gravitational ballet.
In this nice model, is it settled science or still evolving?
It's still evolving, definitely. Newer evidence, like from studying Apollo moon rocks, which record impact histories, suggests this instability might have happened faster than the original model proposed.
Faster? Like how fast?
Perhaps triggered more directly by the rapid evaporation of the primordial gas disk itself, rather than hundreds of millions of years of slow migration. And then there's the intriguing five-planet NICE model.
The five giant.
Yeah, some simulations suggest our early solar system might have actually had 5 gaseous giants, and one got ejected entirely during the instability.
Ejected from the solar system. Could that be?
Could that be the hypothetical Planet 9 that some scientists are currently searching for, based on perturbations seen in the orbits of some distant Kuiper Belt objects? It's a fascinating possibility.
Wow. So our solar system might have kicked out one of its own children. What a dynamic, violent history.
It really highlights the ever-changing nature of our cosmic neighborhood, shaped by these constant gravitational interactions, a story still being refined.
Okay, let's zoom back in on Neptune itself. Among all its intriguing features, its moon system is really unique, isn't it? Especially compared to the other giants.
Absolutely. Jupiter, Saturn, Uranus, they all have these large, regular moons that almost certainly formed right alongside them, from disks of gas and dust swirling around the young planets, like mini solar systems.
Right, orbiting nicely in the equatorial plane, going the same direction the planet spins.
Exactly. But Neptune, well, Neptune's largest moon, Triton, is a complete outlier. Its very existence and its weird behavior tell a really dramatic story.
Okay, what's the evidence telling us?
The evidence overwhelmingly points to Triton being a captured Kuiper Belt object, something that formed out in the icy depths and was later gravitationally snared by Neptune rather than forming with it.
Captured.
Yeah.
What makes scientists so sure?
Several things. The biggest key is its orbit. It's retrograde.
Meaning?
It orbits Neptune in the opposite direction to Neptune's own rotation. That's incredibly difficult, almost impossible to achieve if it formed from the same spinning disk as Neptune. It's like a car going the wrong way down a one-way street.
Okay, that's a huge red flag. Anything else?
Yeah. Its orbit is also highly inclined, tilted significantly relative to Neptune's equator. Plus, Triton is big and dense, actually larger and denser than Pluto, which we know is a large Kuiper Belt object.
Bigger than Pluto. Wow.
And its composition, a mix of nitrogen ice, carbon dioxide ice, water ice, closely matches what we see in other KBOs. Put it all together and capture is really the only explanation that fits all the facts.
So this large KBO, Triton, wandered too close and got caught. What happened then? Was it a gentle process?
Anything but gentle. The aftermath of Triton's capture was likely incredibly violent for Neptune's original moon system.
Oh, Neptune probably had moons before Triton arrived.
Almost certainly. Like the other planets, it likely had a system of regular moons that formed with it. But as Triton was captured, its initial orbit would have been highly eccentric, very elongated.
And that caused problems.
Big problems. This wild orbit likely put Triton on a collision course with any pre-existing inner satellites Neptune had. The result, carnage.
Collisions. Obliteration.
Pretty much. Violent impacts are thought to have obliterated nearly all of Neptune's original regular moon system, shattering them into debris.
Wow, so Triton's arrival basically destroyed Neptune's original family of moons.
That's the prevailing theory. And Triton itself wasn't unscathed. It may have actually swept up and accreted a significant amount of that resulting debris. Maybe over 20% of its current mass came from those shattered moons.
So it grew even larger by cannibalizing the moons it destroyed.
It sounds brutal, but yes. This violent capture and the subsequent sweeping up of debris also played a crucial role in Triton's orbital evolution. It helped circularize its orbit and caused it to spiral slowly inward towards Neptune.
Until it settled where it is now.
Until it eventually settled into its current, tidally locked near-circular orbit. It's a dramatic cosmic event that completely reshaped Neptune's immediate environment, leaving it with this unique, scarred satellite system, a captured king that remade its kingdom.
That is an incredible backstory. And Neptune's story is not just ancient history, right? Things are still happening out there.
Absolutely. It's a dynamic system even now. For instance, relatively recent findings suggest a comet might have slammed into Neptune only about 200 years ago.
200 years. That's like yesterday in cosmic terms. How do we know?
Observations from the European Space Agency's Herschel Infrared Space Telescope detected this peculiar, uneven distribution of carbon monoxide in Neptune's stratosphere. One explanation is that a comet impact delivered a burst of CO and other materials, and we're still seeing the chemical signature spreading out.
A recent cosmic splash.
Yeah.
And Triton itself, is it geologically active?
It certainly seems to be evolving. Its atmosphere is thin but dynamic. It has this discontinuous haze layer extending up maybe 30 kilometers, probably formed by sunlight, breaking down methane into complex hydrocarbons smog, essentially.
Right.
And its surface shows evidence of winds driven by gas released as polar ice sublimits turns directly from solid to gas in the faint sunlight. You see these distinctive fan-shaped deposits.
And plumes, like geysers.
Yes. Voyager 2 actually imaged active plumes like icy geysers erupting from Triton's surface.
Wow. What's powering those? Just sunlight?
That's the big question. The amount of material erupting in these plumes, the mass flux, is surprisingly similar to the cryovolcanic plumes we see on Saturn's moon, Enceladus.
And Enceladus's plumes are powered by
an internal subsurface ocean and likely hydrothermal activity at its seabed, heat from the interior.
So does Triton also have an internal heat source? Maybe its own subsurface ocean?
That's the tantalizing possibility. The similarity to Enceladus is prompting scientists to really re-examine whether Triton's activity is purely solar-driven, or if it hints at an internal heat engine, maybe residual heat from that violent capture, or tidal heating from Neptune.
And if it has an internal ocean, the implications for life.
Exactly. If Triton has liquid water, energy, and organic molecules, which it likely does, it becomes a prime target in the search for life beyond Earth. A potentially habitable world way out there.
That's fascinating. Okay, let's look much, much further ahead now. Billions of years into the future, our sun isn't going to last forever.
No, sadly not.
It'll eventually expand into a red giant.
Yeah.
What happens to the planets then? We hear Mercury, Venus, maybe Earth will be swallowed.
That's the prediction, yes. The inner planets are likely doomed to be incinerated as the sun bloats outwards.
But what about the outer planets, Neptune included? Will they survive?
They likely will survive being swallowed, yes. As the sun enters its red giant phase and later shrinks to a white dwarf, it will lose a significant chunk of its mass through powerful stellar winds.
And less mass means less gravity.
Exactly. As the sun's gravitational pull weakens, the remaining outer planets, including Neptune, will actually migrate outwards into even wider orbits, like a cosmic dance slowly expanding away from the dying star.
That's interesting. And the sun's habitable zone, where liquid water could exist, that also moves, right?
It expands significantly outwards during the red giant phase, yes.
So could places like Pluto or Triton or other Kuiper Belt objects actually warm up?
Temporarily, yes. These currently frozen worlds could be warmed enough to thaw surface ices, potentially allowing liquid water to exist briefly, maybe even temporary water cycles. Distant icy worlds having a fleeting warm spell.
A brief window of potential habitability far out.
A very brief one, cosmically speaking. Because eventually the sun exhausts its fuel entirely. It shrinks down into a white dwarf, a hot, dense stellar remnant. And then, over an almost incomprehensible timescale, quadrillions of years, that white dwarf will cool down and fade into a theoretical black dwarf, a cold, dead star.
And Neptune?
Neptune will become a dark, frigid husk, continuing its slow, ever-widening orbit around that dim stellar remnant for an unimaginable stretch of cosmic time, a silent witness to the sun's long, slow death.
Wow. From ancient impacts to recent collisions, all leading to that distant, cold future. It really shows the continuous evolution of the system.
It's a testament to the ongoing processes, yeah.
Okay, so we've journeyed through Neptune's discovery, its composition, its wild weather, its dramatic history. And let's bring it back home. Why does studying this distant ice giant actually matter to us here on Earth?
Well, beyond the pure scientific curiosity, which is huge, there's a deep connection to the human spirit of exploration.
How so?
Think about Voyager 2's flyby. As experts reflecting on it have said, it's unarguable that the American public and the world got not only scientific data, but images that hadn't been seen before. Images that expanded our cosmic view.
Seeing the unknown.
Exactly. There's this drive, as someone put it, seeing what's over that kind of next hill is something that's very human in character. No other species does that.
And missions like Voyager, they have a ripple effect.
A huge one. A success like that gets the mind going toward tomorrow. It makes us ask, if we can do this, fly a probe billions of miles and get pictures of Neptune, what else can we do tomorrow?
Inspiring the next generation, pushing boundaries.
Precisely. It's a spirit of discovery that technology allows us to uniquely share globally.
And the insights we gain, they're not just about Neptune, right? They're cosmic clues about planets everywhere.
Absolutely. Neptune and Uranus, being our solar system's only nearby examples of ice giants, are crucial for understanding a whole class of planets we now know are incredibly common out there among the stars.
The dominant type of exoplanet, you said.
Yeah, planets larger than Earth but smaller than Jupiter seem to be everywhere. And studying Uranus and Neptune, their atmospheres, their interiors, their magnetic fields, gives us invaluable clues.
Clues about what, specifically?
About how these intermediate-sized, volatile-rich planets form in the first place, and about the physical and chemical processes that shape them across the galaxy. They're like nearby laboratories for understanding exoplanets we can't study in detail yet.
And it works the other way too, right? Studying other planets helps us understand Earth.
Definitely. It's a reciprocal relationship. You could call it planets as experiments. Observations from other worlds can challenge and refine our models here.
Can you give an example?
Sure. Studying wind-blown dunes on Mars using data from rovers and orbiters has actually given us new insights into how sedimentary processes work here on Earth, helping us interpret ancient rock formations better.
Mars teaching us about Earth geology. Cool.
Or consider Earth's magnetic field. We know it's been active for at least 3.5 billion years, which is amazing.
Yeah, protects us from the solar wind. Crucial for life.
Absolutely crucial. But here's the puzzle. The inner core's crystallization, the process thought to sustain the field today, probably only started less than 1.5 billion years ago.
Wait, so there's a gap. What powered the field for the first 2 billion years?
That's the core paradox. It's a huge question in geophysics. And studying magnetic fields on other planets, maybe gas giants or even rocky exoplanets with different histories and structures, might help us figure it out.
How?
By seeing if Earth's long-lived dynamo is normal or some kind of statistical fluke. Are there other ways to power a magnetic field for billions of years? Understanding magnetospheres is critical.
Because without one,
The solar wind can strip away your water and atmosphere over time. That's a big part of why Mars is the dry, cold desert it is today. So studying Neptune helps us appreciate the specific, delicate conditions that make Earth habitable.
okay, this is fascinating. But you also mentioned tangible, everyday benefits, technologies we use, from studying Neptune in space.
Yes. This is where distant exploration truly hits home. Space exploration isn't just about cosmic secrets. It drives innovation that improves life here, often in ways you wouldn't expect.
Like what? Give me some examples.
How about laser eye surgery? LASIK. The incredibly sophisticated algorithms used to fine-tune the complex mirrors of the James Webb Space Telescope needed for those super-sharp images.
Okay.
Those same types of algorithms now form the basis of ophthalmic diagnostic systems used for precise eye mapping before LASIK surgery. It's used in millions of operations worldwide.
Wow. From telescope mirrors to better eyesight. That's amazing.
Or how about life-saving heart pumps? The Micromed DeBakey VAD, this compact device that helps keep patients alive while waiting for a heart transplant.
Yeah.
That came about partly from a conversation between a NASA engineer thinking about fluid flow in rocket engines and cardiac surgeons thinking about blood flow. They realized the underlying principles were similar.
Rocket science, saving lives. Literally.
Literally. Or think about sustainable housing. AI Space Factory learned lessons designing 3D printed habitats for Mars.
Right, the Martian project.
Exactly. They're now applying those techniques and materials to create more sustainable housing structures right here on Earth, called Terra.
Mars tech building Earth homes. What else?
Your phone case. That hands-free, sticky kind, like flip stick.
Yeah, the ones that cling to surfaces.
It uses microscopic fibers inspired by how geckos stick to walls, a technology NASA helped develop for potential use in space robotics.
So gecko feet research for space led to my phone case. Crazy.
It is. Or temperature-regulating fabrics. Material partly developed under a NASA contract for spacesuit gloves called Outlast, designed to manage extreme temperatures.
Okay.
That's now woven into bedding and loungewear to help regulate your body temperature while you sleep. Space tech for a comfy night.
I might actually have that. And water filters.
Big one. Advanced filters developed for the International Space Station to recycle wastewater into safe drinking water. That nanoceramic technology is now used in commercial filters like Disruptor and Pod Plus bottles.
Providing safe drinking water around the world.
A literal lifesaver in many regions, directly from space station needs.
One more.
How about anti-aging cream? NASA discovered this microbe, Bacillus pumilus SFR032, that's incredibly resistant to extreme radiation, like in deep space. Components derived from studying its survival mechanisms are now used in some high-end skincare products and sunscreens to help protect skin from UV damage and potentially slow aging.
From deep space microbes to skincare. That's wild.
It really shows the breadth of it. So the next time you use your phone hands-free, drink clean water, get LASIK, or even just sleep comfortably, remember, you might be benefiting directly from the ambitious quest to understand worlds like Neptune.
It really does enhance our quality of life down here. Safer, more efficient, more connected.
Absolutely.
So as we wrap up this deep dive, we've really journeyed far. From Neptune's prediction purely through math.
A triumph of theory.
To its role in completely reshaping how we understand planet formation and the solar system's chaotic youth.
The nice model, Triton's capture.
And finally, seeing its surprising, tangible impact on our everyday lives right here on Earth through technology.
It connects the farthest reaches to our immediate reality.
It's truly remarkable, isn't it, to think that we've only sent one spacecraft, Voyager 2, on just a brief flyby over 30 years ago.
It's just one quick look.
And yet, our understanding of Neptune has expanded so dramatically since then through clever observation from afar and sophisticated modeling.
It shows what we can deduce even from limited data. But so many profound mysteries still remain about this distant ice giant and its strange captured moon, Triton.
We still don't fully grasp that internal heat source, the temperature anomaly.
Nope, that's still a big puzzle. Why does it radiate so much heat compared to Uranus?
And the potential for that subsurface ocean on Triton.
That's huge. If confirmed, it instantly becomes one of the most compelling places to search for life beyond Earth in our solar system.
So thinking ahead, what might the next dedicated mission to Neptune reveal, if we ever send one?
Oh, imagine a dedicated orbiter, maybe even a probe into Neptune's atmosphere or a lander for Triton. The discoveries could be revolutionary.
We could finally understand its interior, its weather patterns up close, maybe even find evidence of that ocean on Triton.
It wouldn't just tell us about Neptune and Triton. It would tell us more about ice giant planets everywhere, about the conditions for life, about the history of our solar system.
And ultimately about ourselves and our place within this vast, incredible cosmos. It really leaves you wondering what secrets are still waiting out there.
Absolutely. It's a journey that's far from over.
Thanks for listening to All in All.